So welcome to week 7 of the tutorial on advanced quantum mechanics and applications. I'm Kaustubh Mukherjee from IISER Bhopal, and this week's tutorial will consist of mainly on variational principle, which was formally introduced in this week's coursework, and we'll be take on some WKB approximation problems as well. So the first problem that we are going to deal with is to find out the binding energy of hydrogen atom using a Yukawa potential. So what we are going to essentially find out is binding energy of hydrogen atom using Yukawa potential. So we are going to take two problems on variational principle which deals with hydrogen atom, and then we are going to go for some WKB approximations. So let us first look at what is Yukawa potential, and then we can move on to solve it. So Yukawa potential is defined as your VR minus square. So it is similar to what you have it in a Coulomb potential, but we have an additional exponential here. So this is the extra term compared to the Coulomb potential that we generally have in a hydrogen atom. Okay. Now here the mu is given as m gamma c by h bar, where your m gamma is mass of photon. Okay, so what we know from variational principle is that we have the expectation value of Hamiltonian given as T plus V. This is T is the kinetic term and V is the potential term, and what we have to do is we have to minimize this term to find the energy, the ground state energy that we get for any wave function that you choose. So since the potential here is new, so what we are going to essentially do is we are going to choose a wave function which is that we already are aware of is a wave function for ground state atom, the hydrogen atom. So for hydrogen atom, your wave function is written in the form of pi a cube e to the power minus r by a, but we are going to change it here to b cube. So we are essentially changing a into b, and here b is a parameter which we are supposed to optimize. So we are going to minimize the h minimum through by del b, which is supposed to be 0, and b is the parameter here that we are going to do the optimization of, right? So we know that this wave function is your ground state wave function for the hydrogen atom. So if we didn't had this term which comes from the Yukawa potential, then we would have essentially got the ground state energy of the hydrogen atom. But for Yukawa potential, we are going to see what we get here. Okay, so first term is let's say we find the potential term, which is here. So your V here is defined on the top as this. So this is nothing but psi star r. I'll write it here also. V psi of r d cube r, and we are going to put the potential here. So this is already normalized wave function, so we don't need to normalize it again. Okay, so we put e square by 4 pi epsilon naught. We have can take out 1 by pi p cube outside, and then we have our e to the power minus 2r by b. Just let me know if there are any questions. I hope I am audible. Okay. So to the power minus 2rb, and we have the potential e to the power minus mu r by r, and since this is d cube r, that is spherical coordinate, so we have r square sine theta dr d theta d phi. Okay, sorry. Right. Now since there is no theta dependence, we already know that sine theta d phi gives us a 4 pi, so we can directly take the 4 pi out from there, and all we have to do is integration of e to the power minus 2r by b. Okay, so this part can actually be summed upon, so we have minus mu plus 2 by b r, and this cancels out, so we have r dr. This goes from 0 to infinity. Okay. Now, so there is this famous formula that I hope everyone is well aware of, which is very useful in everywhere, in every case. So when you have something in the form of exponential to the power alpha x to the power n, there the minus sign is also there, and you have an x to the power m polynomial with it dx, then there is a generalized formula for this. So alpha n plus 1 m, and there is a gamma function of n plus 1 m. Okay. I think this is the opposite. This m plus 1 by n plus 1 by n. Right. So this gamma function is nothing but your factorial, which I believe you all are well aware of. And one other useful tool is gamma half, we know is root pi. Okay. So whenever we have n equal to 2, then mostly we will get a denominator 2, and you can get all 3 by 2 or 5 by 2 using this. Okay, so gamma 3 by 2 is nothing but your gamma half into root pi. Okay, so this is a very important formula and is used widely across the whole physics, whether it is statistical mechanics or quantum mechanics. So you can just keep this as your prime note somewhere of the essential formulas. Okay, now using this formula in the integration above, what we get for the expectation value of b, 4 pi by b cube. So we have mu plus 2b as our coefficient, which will come down 2 by b, and the power will be 1 plus 1 by 1, so this is square, and here we have a gamma 2. So gamma 2 is your nothing but, so gamma n is n minus 1 factorial. Okay, should put this, okay, I cannot put this one. So this is nothing but 1, right? So this is what we get from the integration, and hence we can write it as, did I miss something? Okay, we can just simplify it further. You can cancel this part. 4 by b cube, you can take the b by 2 out, so what we are taking is b by 2 whole square out, and we get a 1 plus mu p by 2 whole square. So this simplifies a bit, does nothing much. Sorry, not b by 2, 2 by b. So your this part gets cancelled out, your b square cancels the cube, and we end up getting minus e square 4 pi epsilon naught 1 by b 2 plus mu by 2 whole square. Okay, so this was the what do you say, your potential part. Now this part. Now for kinetic term, so there is some tricks. So like some in the some of the previous chapter you might have done some virial theorem in which you sort of find out that your kinetic term is En, and this is also minus En. This is also the double of 2v, something like that. Okay, so what we are essentially going to use is the same trick here. We are going to use expectation value of kinetic energy given as minus E1, which is if you want the proof, then I can give you the proof. You just have to look at it, and this is given as this. Okay, so together we get the expectation value of Hamiltonian in the form minus e square 4 pi epsilon naught b plus mu b by 2 whole square. And what we are now supposed to do is minimize this Hamiltonian. Okay, so your H minimum we have to find out through taking the derivative of del H by del B equal to 0. So let's just do the derivative. This can be d also, it's not partial actually. Okay. So taking the derivative, what we get from the first term is nothing but your 2 h bar square. So there is a minus 2 mb cube, 2 gets cancelled out, and there are 2 b terms here, so we can deal with them one by one. So we have e square 4 pi epsilon naught b. So first we do for the b, so we get a minus 1 by b square mu b by 2 square, and for the second term we again get minus, there is a 2 b 1 plus mu b by 2 cube, and the coefficient of b is mu by 2. This gets cancelled out, and we end up getting this part. So simplifying, minus h bar square by m b cube, and so minus comes out, this becomes plus 4 pi epsilon naught, taking the common factors out. So there is a b square, and there is 1 plus mu b by 2 extra, plus there is a mu factor here, plus mu b, and we have b square 1 plus mu b by 2 whole cube. Alright, now so you just have to put this to 0. Okay, so what we get, so we can take this term on the right or the other way around, whichever you prefer, it's fine both ways. So you get e square by 4 pi epsilon naught 1 plus 3 mu b by 2 by e square plus mu b 2 whole cube, and this b square cancels the cube here, and we only get a b. Now our main motive is to find out the b, right? So let's take the b on one side and put all others on the other side. So we have 4 pi epsilon by e square square by m, and on the other side we have b plus mu b by 2 1 plus mu b 2 whole cube. So there is a 3. Okay, now this is a bit what do you say, a complex equation to solve, right? So let's say this term is nothing but your a, so we have to solve this in terms of a, let's say. And to solve this we have to take an approximation that mu is very very smaller than 1, okay, because this is a cubic equation and it can be it can get difficult to solve. So to get a simplified solution to it, we consider mu to be very much less than 1, okay. So we can use the binomial expansion for that matter. Now once you have so we have b 1 plus 3 mu b by 2. Let me just check if I'm heading in the right direction. Yes. Okay, so one thing is for sure. So if you, let's say if you have mu equal to 0, so what you essentially get is b is equals to a. So that means under the condition when mu is not present, your b is equal to a. So you can also get a rough analogy that if mu is almost equal to 0, then b is also almost equal to a. That is what you are supposed to get in the end, okay. So just taking the approximation and using it here. So what we have, so you can take the 3 okay, let me just write down as it is for the first step. Minus 3 equal to a, and then we can do the expansion. We have 1 minus 3 mu b by 2 in the next coefficient it's 3 by 2, sorry, yes, it's 3 mu b by 2 plus 6 mu b by 2 whole square, and this is equal to your a. So this is also not exactly equal since we are taking an approximation, and it's almost equal to a. Now taking only the terms that are, let's say, up to square, okay, so if you have minus 3 mu by 2 and plus 3 mu by 2 mu b by 2 will be cancelling out, and we have 9 by 4 mu b square, and we get a 6 by 4 mu b square, and we just ignore all the higher order terms, okay. So what we get from here is your b 1 minus 3 by 4 mu b square equals to a, okay. So this is still, sorry, okay, so this is still the second order only. Now since again this is a second order term, you can actually say for the mu square, so this is again will be almost equal to 0, and as we held our approximation, you can say that b is almost equal to a, so we can actually deal it in the reverse. So since we have to ultimately optimize b, so we can actually write in terms of a now, okay. So your b is nothing but a by 1 minus 3 by 4 mu b square, and this you can write in the form 3 by 4, so this gets plus taking the same binomial type expansion, and you get a mu a square, okay. So this is what your b looks like in the end, okay. So we are going to use this substitute the b in the h minimum, okay. So we have h minimum in this form, okay. So here is h, this term we need, and we are going to substitute the b here. So let me just take this part down and substitute the b here. So we have 1 minus b is given as a 1 plus 3 by 4 square. Similarly, here and here we have to substitute. So I will keep this away. We have 1 square, and similarly you can actually substitute directly with a here, because under the extreme condition of mu square we have your b is almost equal to a. So wherever there is only a linear of b, you substitute, and where there is a square already, then you can just put it as a directly. Okay, now the minimum that we get here, 1 by a square minus 3 by 2 mu a square, taking the same binomial, 4 pi epsilon naught. Here we have 1 by a, 1 minus 3 by 4, and 1 plus mu a, I suppose. Okay, so this is minus 2 by 2, and then we have 3 mu a by 2 whole square, the third term. Okay, so once you have these, then you can do a Taylor expansion, sorry, not Taylor expansion, just simple algebraic multiplications. To square, so this remains as it is, and you only take up to the second order here. So what you have is 1, you get minus mu a, then there is minus 3 by 4 mu a square, and you have a plus also. I think this is 3 is outside. Mu a by 2 whole square. So you get a 3 by 4 mu a square and all the higher order terms, which we don't care, and these essentially gets cancelled out. So what you end up, okay, now here we consider the kinetic term and the potential term that I previously mentioned that you get from the virial theorem. So there you get your T as minus E1 h square by 2m a square, and you get 2 E1 as your V, which is nothing but minus E square by 4 pi epsilon naught a. This you get from the virial theorem applying on the hydrogen atom. Okay, so you substitute these as the E1 wherever this is possible. So what you end up getting is you get a E1 minus E1 here with 1 minus 3 by 2 mu a square, and you get plus 2E1 1 minus mu a. Okay. So from here on, simply just algebra square plus 2E1 minus 2e1 mu a. So this is nothing but your e1, you take it common, so 2e1 minus e1, you get a 1. Then you have minus 2 mu a, and finally 3 by 2 mu a square. So this is your H minimum for the Yukawa potential. Okay. Now for the second part, okay, now second question deals with the same hydrogen atom, but we are like it's a pure hydrogen atom, but we are going to take a different wave function, just a test case scenario. So like a trial wave function, what we are going to do is we are going to consider r as a e to the power minus b r squared, which you know is a Gaussian and mostly a ground state for the harmonic oscillator, but we are going to check the ground state energy that a Gaussian gives in the case of hydrogen atom. Okay, so for that purpose, so you already know about the Hamiltonian for the hydrogen atom, which is your square 2m del square minus e square by 4 pi epsilon naught 1 by r. So this is the Coulombic term, and first one is the kinetic term. Okay, and after this we are going to take on some WKB approximation questions. Okay, so this will be the last on the variational principle. Okay, now to first we have to normalize the wave function. As you can see, it is written with a e to the power. So this is the variable parameter that we are supposed to optimize with taking the differentiation, and a is the normalization constant. Okay, so first to normalize it, what we have to do is equal to 1. Okay, so what we have here is mod a square, so mod a square e to the power minus 2 b r square sin square theta d theta d phi. There is dr also. Okay, so since there is no theta, we can just take it as 4 pi outside. We have e to the power minus 2 b r square dr equal to 1. And this, as I said previously, that there is this powerful tool that you can use. So here we use the same. We have minus alpha x to the power n and x to the power m, right? So here n is equal to 2 and m is also equal to 2. So what we get is 4 pi mod a square 1 by 2b m plus 1 3 by 2 comma 3 by 2 equal to 1. So this yields us, we just take everything on the other side. So this is nothing but your root pi by 2. Okay, so taking to the other side, you get 2 by root pi 2b 3 by 2 by 4 pi. So this in so this is nothing but 2, we get 2 cancel out by pi 3 by 2. So this is your normalization constant. Okay, this is square, so we get a as 2b by pi 3 by 4. Okay, now your finding out the kinetic term and the potential term becomes easy because of the integration that we already bookmarked. So we are going to use that very much here. Okay, so for v we have psi star r v of r psi r d cube r. So we get a mod a square outside, that's a constant term anyway, and we just place all other terms. So we have psi as e to the power minus br square, which becomes, the two of them combines to become e to the power minus 2br square. We can take the 4 pi out and we just have the r square here. Okay, so we then have e square by 4 pi epsilon naught r minus r square dr. So we can take all the coefficients out actually. Mod a square 4 pi minus e square by 4 pi epsilon naught, and the integration becomes e to the power minus 2br square r dr. And using the same putting the mod a square, sorry, this seems to be stuck. Just a second, let me stop screen sharing. It's working now. Right. So we put the mod a square, which is 2b by pi 3 by 2. We have e square epsilon naught, and from the integration we get 1 by 2b is 2 is 1. This is nothing but 1, so we have 1 over here, 1 plus 1 by 2, which is 1. So ultimately we get, okay, am I missing something out? Four pi supposed to be kept, so get 4 pi by 4b. Let me keep the terms as it is. Okay, so what we have here is e square by 4 pi epsilon naught. We have 4 pi, we get 2b 1 plus 1 by 2 is 1, and we have 1 here, I suppose. So okay, right. So we have 2b cancelling one of them out, so we have 2b to the power half, and there are too many pi's, so we have pi half e square by 4 pi epsilon naught. This cancels, so somehow it's supposed to be 4 pi by 4b. I'm not sure where I'm missing a 2 factor. The ultimately what we are supposed to get is something like Okay, so 2 is actually cancelled out. Sorry about this mess. This 2b is already cancelled out with the 2b half. Okay, so that remains 4 pi epsilon naught. What we essentially get is 2b by pi. Right, we have a pi cancelling out. There is 4, and we have this 2b that is already cancelled out since we have to the power half here. Okay, so this is what we get for your potential term, and for the kinetic term we have 2m mod a square per minus br square, and we have a delta nabla, the double derivative, sine theta dr d theta d phi. Okay, now to calculate the derivative, we can, since it only depends on r, we don't need to consider all the other factors, that is the theta and phi. So we only have to take the derivative with respect to r1. Okay, so this essentially we get d by dr, we have r square, we get minus 2br e to the power minus br square, done. And then we have, when we take the derivative, so we get r cube here, so let's take the minus 2b outside. Okay, so minus 2b is outside, we have r cube which gives us 3r square, and we have r cube remaining with minus 2br e to the power minus br square. Right. So what we essentially get, since there is r square in the denominator, we get minus 2b 3 plus r square minus 2b r square br square. I hope so. Oh right, exponential is common. Sorry, I can make this up. Right, thanks. Okay, so what we do next is we just put this into the integration. So what we have here is, we shrink it, minus h square by 2m mod a square, we get e to the power minus 2br square minus 2b is 2br square, and r square, we can take the 4 pi out since there is no separately dependence on theta and phi. Okay, so since will be okay, fine, I'll just do it. So what we essentially get, we get minus 2b outside, we have 3 minus 2b square, and we have a r square already at place. Okay, so we have h square by 2m mod a square 4 pi. There are two terms mainly, we can take the 2b also outside, minus already done. So let's say minus 2b r square, 3r square is one term, the other one is minus 2b r to the power 4 dr. Okay, so this term gives us 3 by 2b to the power the gamma function is 2 plus 1 by 2, which is 3 by 2 gamma 3 by 2, and this one gives us 2b by 2b to the power 4 plus 1 by 2, which is 5 by 2 gamma 5 by 2. So you can do the algebraic calculations, and we ultimately end up getting by 2m 2b by pi 3 by 2 4 pi 2b, and let's just write down the simplified part, which is 3 by 8b we get. Okay, 3 by 2b by 2 Okay, I'll just write down the final term here. It's getting a bit messed up. So finally what we get, you can find in the notes, so 4 pi b 2b by pi 3 by 8b. If you find any anomaly, just let me know, we can try to figure it out. Final term is by 2n. So we have got the h complete now with the t plus v, so by 2n plus v plus your minus e square by 4 pi epsilon naught 2 root 2p by pi. So taking the derivative with respect to b, we get 3h bar square by 2n minus square by 4 pi epsilon naught 2 by pi by root b to the 0. So your root b essentially comes out to be something like 4 pi epsilon naught 2 by pi 2n by 3h bar square. Just taking on the other side, nothing special here. And you can put them in your h minimum. Okay. You get 3h bar square by 2m by epsilon naught whole square 2 by pi 4m square by 9h bar to 4. Okay, some very complex terms. Okay, so I'll just get to the ultimate message that we get here is something of this sort without wasting time. This is you can check by yourself this result. So the ultimate result is that we get something like 8 by 3 pi E1, which if you put all the values in of the ground state, so we know the ground state of your hydrogen atom as minus 3.6 eV. So this essentially gives you something around 11.5 eV, which is of course above the ground state. So we know that through variational principle we can never get below the bound state. Whatever energy that we get from the ground state, sorry, not bound state, the ground state. So whatever energy we get from any trial wave function will always be above the actual ground state. So here also we get another proof of it. Okay, so I'll just go through the WKB problems. So this took a lot more time than I had anticipated. Okay, so you have already formally introduced the WKB in your lectures, in which you must have seen that there are potential wells, and there is some, instead of a flat well, you get some smooth function, a slowly varying function. And you can apply the WKB approximation at certain regions which are far away from the turning points. So when you have, let's say, energy E, which is essentially somewhere here, and this makes you classically impossible to go through the potential well, right? Which you can do in a quantum mechanics. You can tunnel through the potential well, but this is not possible in classical, and we call them, these points, as a turning point. And near these turning points, these WKB approximations are not valid, but in the regions which are far away from the turning point, you can actually implement this WKB approximation. So we are going to take on some problems which are like, you can actually imagine it in the real world scenario. For example, bouncing off a ball. Okay, so when you have a ball, let's say you keep the ball at a height h. Okay, so you know that this ball, so let's say it's a quantum ball, we go into the quantum world, and this is an infinite potential well. Okay, that means there's a wall and the ball cannot penetrate through the wall. Okay, you throw the you just leave the ball, it will go and bounce back, right? So this is the classical world which we can actually mimic in the quantum world, and we can see how the wave function that one gets is actually relevant to the WKB or the Aries functions that you have seen in the WKB problems. Okay, now the potential, so let's just draw the potential ones. So you are already familiar that for gravity, under the approximation that the R is much less compared to the center of the earth, we get a potential something of the sort mgx, where x is the distance from the surface of the earth to the height where the ball is kept, right? And this we can draw as it's a linear function, so we get p of x in this form. Okay, and on the negative direction we have nothing, so we essentially get a infinite potential here, and on the negative side there is no particular potential except for the infinite one, which is good enough in itself, right? Now, to find the wave function for such case, what we have to do is the Schrodinger equation, right, which tells us that minus h bar square by 2m, so we don't really need del square here, since it's a single dimension problem. We take d square by dx square psi plus mgx psi equal to your energy. So we say, let's say your energy, so since the initial height was h, so your energy is essentially mgh, which you are already familiar with, and let's say this h is somewhere here. Okay, now in order to solve it, okay, so what we do is essentially collect the similar type of terms on one side. So we have d square, and we take all the other on the other side. We have mgx minus e. absorbing the minus sign. Okay, so now we can take the mg out, and what we essentially get is 2m square mg x minus e by mg, and this part you can substitute with a variable y. Okay, so if y equal to x minus e by mg, your dy is nothing but just dx. Let's say straightforward substitution. Okay, this is again stuck for some reason. Alright, so straightforward we get d square by d y square as, and let's say this is some constant alpha, since all of them are constant, so we can actually write it in the form alpha y. Okay, let's say this is alpha cube. Okay. Alpha y and minus this psi, and we have a psi here, right? Now the next substitution that we need to consider is z equals to alpha y, and so what you get, dz by dy is alpha, and d psi by dz is nothing but, so we have to find the double derivative here. Dy dz, this is nothing but 1 by alpha d psi by dy, and for the double derivative you just repeat the thing one more time. One plus alpha d psi by dy. Okay. Alpha you can take out, and this is again dy d psi by dy dz by dy. So what you get is nothing but 1 by alpha square d square psi by dy square, and you just substitute into the equation 1. That's it. So what you get is 1 by alpha square d square psi by dy square, and on the other side we have alpha cube y, so alpha y is z, so you get alpha square, okay, sorry, this is supposed to be z, and we are supposed to take the alpha on the other. Okay, just taking the alpha on the other side, right? And we have z psi, so your alpha square gets cancelled out, and you end up getting a familiar equation which you must have seen in the lecture of the for the WKP approximation. And the general solution for such wave function is given in the form of your Airy's function, which are aiz plus biz, and from the definition of the function it is it is given that this term blows up at large z when z tends to infinity, so this term cannot be present, and hence based on this condition you only get a ai of z, which is your, you can actually substitute, which anyway is not necessary. Okay, so this is your wave function for a bouncing ball, a ball which is under the gravitational potential, and this you can actually find out in the quantum world as well. Okay, now in order to find, let's say, the energy, okay, so if you want to find the energy values for such case, what you do, okay, so for WKB approximation, I'll write down the 3 rules that are absolutely important. Okay, so you just have to keep these in mind. So let's say when you have a two-sided wall, these can be very helpful for any competitive exams or any other exams as well. So these tricks are very handy. For one-sided wall, you have 0 to a p of x d of x by pi h bar, and when there is no wall on any side, the WKB approximation is your n minus half pi h bar. Alright, so in this case there is a one-sided wall, so we only have to apply this formula. So, and our a is nothing but the h height, right? P of x d of x dx n minus 1 by 4 pi h bar. So to find the energy, what we have essentially have to do is your p of x is given as root 2 me e minus mg x, right, where your e is mgh that you are already aware of, right? Now so to integrate 0 to h to m e mgx dx, this is what we are supposed to find out. So you can easily substitute e minus mgx as y, and you get dx equal to dy minus mg, right? Okay, so what you end up, let's say this is I, so you get your I as 0 to h root 2m, you can take that out, and you have, sorry, this is not h anymore, let's say this is some y1, you have root y dy minus mg, and what you get here is minus mg y 3 by 2, and you get a coefficient of 2 by 3, 0 to y1. So this essentially gives you minus 2 by 3 root 2 over m 1 by g. You have e minus mgx from 0 to h, right, to the power 3 by 2. Okay, so what you get e minus mgh to the power 3 by 2 minus 0 e to the power 3 by 2. Now we know e is equal to mgh. So this is actually getting cancelled out, right? And minus minus sign goes off. You get 2 by 3 root 2 by m e 3 by 2 by g. And on the other side we have n minus 1 by 4 pi h bar. So the energy of this ball is essentially E on n is given as three by 2 g root m by 2 n minus 1 to the power 2 by 3. So these are the energy of the levels. Okay, and similarly you can also do for a potential, the harmonic potential. So let's say you have a harmonic potential and you want to find out the energy levels En, right? So you are already aware of the energy levels based on the past calculations that you have done. And let's say the energy of the particle is E, which is, so here it is, let's say it's x1 and here it's x2, and the potential you are already aware of is V of x as half m omega square x square. So at so your x1 is, x2 is nothing but your x1, which is your E. So let's say E is your half m omega square x2 square. So you get x2 as 2e by m root over and 1 by omega on the outside. So this is 1 by omega root 2e by m. Okay, so these are the turning points. Now so based on the tricks that we have here, so let me just copy. So since there is no ball here, so we are going to use the formula. So these three formula are the prime formulas for WKB. You don't need to know anything else for any particular, like for competitions or for your exams as well. Okay, so here x1 and x2 are essentially this one given here, and your p of x is nothing but root 2m e minus v of x, right, which is 2me minus half m omega square x square. Okay, now in order to do the integration for such case, what you have to do is, so there are plenty of tricks for that. So what essentially get here is, so you take the m omega out, you integrate from minus x2 to x2, and you essentially integrate 2e by m omega square minus x square dx, and this part is nothing but your x2, okay, which we have seen, x2 square. Okay, so you get x2 square minus x square, and this is essentially a even function because for minus x as well as for plus x it will be same, so you can actually make it from 0 to x2 with the 2 factor on the outside. Okay, and the integration of this you can find it out on the internet as well, so I'll just write it down directly. It's given in this form, or I believe you might have already done it in your previous courses. So we have 0 to x2, and putting in the values you get x2. If you put x2 here, this is 0, so this term is anyway 0, it does not matter what you do with it. And for the second term you get x2 square sine inverse 1 x2 by x2 minus sine inverse 0 is 0, so it doesn't matter, right? And your sine inverse 1 is nothing but pi by 2. So putting this, you get x2 square pi by 2. And finally, since on the other side you had, is it getting stuck? Just a second. It's almost done. Okay, now so you put in the values, that is 2m omega square, you have 1 by omega square, 2 x2 was your 2e by m, suppose 2e by m into pi by 2, omega gets cancelled, m gets cancelled, and you essentially remain with, let me see some factor, pi e by omega. Okay, and on the other side you had n minus half pi h bar, so your pi gets cancelled out. What you essentially get is n minus half h bar omega, and for this case the n goes from 1 to, now if you have like change the n from 1 instead of 1, it goes from 0 and so on, it becomes en equal to n plus half h bar omega, which you are already familiar with in other cases as well, in the other way of solving it. So yep, so this is the last problem that we had considered for this tutorial. If you have any question, you can ask, or we can just conclude this session here, and thank you for joining. Okay. Thank you for joining. Take care.